Hello, I'm glad to see you again at the next meeting of our Modern Dynamical Systems course. And today will be the last lecture that is partly dedicated to some aspects of Teichmüller dynamics. Namely, we will conclude the part about the ergodicity of Teichmüller flow, and also I will simply mention, without any proofs, some other results that are famous and important in this field, just to give you the idea, for instance, why the Fields Medal was awarded several times to people who worked in this area and around. And the second part of our lecture, we will switch to a completely different branch of dynamical systems. Namely, we will start to study homogeneous dynamics. We already mentioned it a few times when we were studying the dynamics of the geodesic flow. And I hope that we will have enough time and resources to get some familiarity with this very exciting part. And if we will be fast and successful, at the very end of the course, we will be back to Teichmüller dynamics, where I will show you how to use the ideas from homogeneous dynamics in some contexts important for Teichmüller 1. Namely, you will be back to the work of Mariam Mirzakhani, but you will study a different part of it, not the one that Sergei Konstantinovich observed in the last two lectures. So today we start first with the ergodicity of Teichmüller flow. So I recall you some of our notations. We defined the following sets on the one of the previous lectures when we discussed why interval exchange transformations are typically uniquely ergodic. So delta was our parameter space, and we considered that the simplex and projective space, pi the permutation responsible for the combinatorial aspect, and then delta pi was responsible for the suspension. And I recall you that theta pi, sorry, not delta, but theta pi was responsible for the suspension. And I recall you this is positive, and this is negative when you take p bottom. This is less than 0 when we have k between 1 and d. So we also associated S star with this thing, and S star, first we defined S star gamma. These are just notations that you have already seen, but since it was 3 weeks ago, I recall it now. But if you are lost a bit, you can go back to what we discussed at the previous time. So we have a section of this parameter space saying that this is a part of S gamma when T alpha is positive. And then we consider all the arrows of our D. We take a union of on all arrows, and we get S star D. And then we consider the Teichmüller flow and some first return maps of this flow to the sections that we mentioned here, namely the return to S of D, first return map we defined by V. V is named in honor of Vich. And to C star D, we return with the map V star. And so the plan is to show that V and V star are ergodic, and in such a case we know that the original maps should also be ergodic, and so it will be enough to understand that the Teichmüller flow defined in M1 of D is also ergodic. Now we apply Birkhoff ergodic theorem that you already know. We discussed it, even if nobody finally gave a talk about it, but still We mentioned it when we discussed the ergodicity of geodesic flow. So it's still our key instrument. And Birkhoff-ergodic theorem gives us the following statement, that for any continuous function phi on S star of D, there exists almost everywhere defined function phi with a bar such that for almost every set of parameters that are given by the length of the interval exchange transformation, its suspension at the permutation, the one that lives in S star of D, we know that the lim, and n goes to infinity, 1 over n, 0 n minus 1, phi v star m lambda tau is equal to phi bar p lambda tau. And the same thing holds if you replace the forward orbit by the backward orbit. This is a direct corollary of Birkhoff-ergodic theorem, and then what distinguishes ergodic theorems, ergodic functions from non-ergodic one, is what we can say about this phi bar, about this limit. Because if the function is ergodic, you are supposed to have a constant almost everywhere here. While if it is not, you can have whatever function. So our strategy to prove ergodicity is to show that this phi bar is almost everywhere a constant. So for any continuous function, does not matter who is phi, you will have a constant here. So the plan is the following. First we erase the traces of mechanics, and then we start to execute our strategy. So we take a point, almost any, and so we know that we can iterate Rosy-Veach induction. It is defined. And what is cool about Rosy-Veach induction, if we consider just the Rosy induction, the path on the interval exchange transformation itself without suspension, then you only have a forward orbit for this map. But if you deal with the band complex, with this two-dimensional thing, you can define forward and backward orbits. Because you remember what happened with the length of the intervals. While the horizontal lengths of the intervals were decreasing, the length of these bands, they were increasing in a similar way. So, and these two processes were dual. So in a similar way, you can define the backward orbit. You just switch the roles of these two things. So there is a way to see it as a kind of algorithm and an inverse algorithm to itself. So you have a B-infinite path. And this is gamma. You split it into two parts. One is responsible for the direction forward one, so you apply it to the permutation and the length of the horizontal interval, and one you apply to this vertical length. So you have a B-infinite path on the Rosy diagram. Now we can apply a Poincaré recurrence theorem, which is our second magic wand together with Birkhoff-Ergodic theorem. And so we know that due to this fact, due to existence of this theorem, we have a piece of the path. So there is a finite piece, finite path, such that it has shares the end of gamma minus. Gamma minus such that all coefficients of the corresponding Rossi matrix are strictly positive. You remember this was a theorem proved by Marmy, Musa, and Ducos that concatenations of several complete paths, it necessarily gives us a positive path. So it's enough. And we can also assume that this gamma E appears infinitely often in our gamma. And here is where we apply this Poincaré recurrence theorem. Now I recall you that when we studied the measures, we introduced a cone, which was an open set in P R alpha. It was an image of positive cone in RA, and we associated a Hilbert metric with it. It was our tool to prove unique ergodicity. Maybe you remember that we used it in order to show that the corresponding map is contracting, and that's why we had only one fixed point that corresponded to this special unique measure. So we already know who the metrics are, and we have this metric. And now what we do is that we consider 2 points that would live at the same part of the parameter space, and then we consider the length of the intervals that we get when we apply our algorithm in a backward direction. So these are the length of the intervals that we have when we apply V star minus M and V star minus M to the same thing, but we replace it by lambda prime. So as before, as when we studied the unique ergodicity, we will have the following thing, that the lim of the distance between these 2 points, once we iterate, is 0. We go closer and closer to each other. We have a contracting map. And the motivation is completely the same, because we use this positivity. And so what we get is that then we can be sure that this phi, with bar that we defined here, it does not depend on lambda. So this function does not depend on lambda. Now the idea is to try to use the duality between lambda and theta, the fact that Rosevich induction is equally respectful towards the horizontal length and the vertical length, and so try to apply the same argument and show that nothing depends on tau either. So if we will be lucky enough, we would be able to show that we have ergodic map due to the second part of the ergodic theorem. So let's try to execute it. So we fix the point. It's a generic point. And we want to find a path gamma S at the beginning of gamma plus. That will be the analogous of this gamma E. Beginning of gamma plus. So it should appear infinitely often at gamma plus. And at the same time, we want that we have a positivity, so we will guarantee it like that. P prime here is an endpoint of this gamma S. Once again, the fact that this path appears infinitely often is guaranteed by Poincaré recurrence theorem. So this part, we just repeat the logic that was established by Marmi-Moussaïekos. And then we can be sure that using Hilbert metrics relative to these open sets images, we conclude that our function does not depend on tau as well. So indeed, it's a constant, almost everywhere. And at the same time, we know that this phi bar is V star invariant, so we know that phi bar is constant almost everywhere. And then it remains to prove that this condition is satisfied. The rest we all checked. So in order to prove this condition, we need to establish an analog of Marmi-Moussaïekos. And the only delicate point is that, thinking Marmi-Moussaïekos, we needed 2n minus 3 copies, and here we need 3d minus 4, where d is the number of intervals. 3d minus 4 complete path. But it's a technical lemma. And for the rest, everything works as I announced. So now, due to this fact, we are able to make the final statement. So we know that V star, they are all ergodic. And thus we know that the restriction of the Teichmüller flow to any component of the marked modular space is necessarily ergodic. And thus the action of SL2R on any such a component is also ergodic. This completes the proof of ergodicity of the Teichmüller flow. So it follows from the fact that we checked that Rosevich induction that is seen as a first return map to some cross-section of the modular space is ergodic, and thus the whole flow is also ergodic. Now there will be a very short section when I try to outline some famous results in about interval exchange transformations and their relatives. I will not prove anything at this part. I will just tell you more or less what kind of statements people tried to show and what they are working on now. So the first thing I want to show you is about weak mixing. So first, let's forget for a moment about interval exchange transformations, and we will think about abstract measure preserving transformation in a probability space. So this is a measure preserving. XM is a probability space. So what does it mean to be weakly mixing? Is the following thing: that you take any two measurable subsets, they're measurable, and you consider the measure of the intersection of pre-image of A with B, and you compare this measure with the product of measures of A and B. You sum up this over all the K, and you add averaging. And so you consider such a limit. And you claim that this limit is 0. So this is what is called weak mixing. Just to compare, what is a strong mixing? So this is a weak mixing. And the strong mixing is the following thing: that you do a similar statement, you consider this guy, and you want that it's directly a product. So you don't add any averaging, and you want it to be equal as a limit, of course. And this is a strong mixing. So it's an exercise to check that strong mixing implies weak mixing, but the opposite is not true, and that weak mixing implies ergodicity, but the opposite is not true. So every time you increase the level of your requirements toward the mixing abilities of your map. And the theorem about interval exchange transformations in this context, there are two. One is that interval exchange transformations are never weakly mixing. Sorry, I never mix strongly mixing. Sorry, made a mistake. This is by Katok in 1980. And more or less at the same period, Katok and Stjopin showed that if you consider interval exchange transformations just on 3 intervals, then it's enough in this case, you can show that almost all interval exchange transformations are weakly mixing. And so there was a conjecture that typically they should be weakly mixing. They are never strongly mixing, but they should be weakly mixing typically. But it took a lot of time to prove this theorem. And finally, the following result by Avila and Forney appeared. 2007. So we fix a reducible permutation. And we assume that this permutation is not a rotation. Rotation just means that the order of all members, all the numbers in your permutation is preserved. So things like 1, 2, 3, 2, 3, 1 is a rotation. But if you change somewhere the order with respect to each other, it's not rotation anymore. So if it's not a rotation, then for almost every lambda, F lambda pi is weakly mixing. So Katok-Stepin proved this thing for 3 intervals. The proof of this theorem is very complicated. It requires both a very accurate analysis of what's going on with the corresponding modular spaces and combinatorics of the permutations that you have. You need to work with the Rossi diagram. And at the same time, you have to use a lot of some analytical tools. And it all is based on a very general observation that actually for any invertible measure preserving transformation, to be weak mixing is equivalent to the fact that it has continuous spectrum. What does it mean to have a continuous spectrum? It means that only eigenvalue is 1. And the only eigenfunctions are constant. So you can also extend this theorem by Avila and Forney to the framework of flows and the translation surfaces. And that's what we're going to do in a second. So the theorem, also by Avila and Forney, is the following. You take any stratum of the modular spaces of translation surfaces. You don't want to work with tori, all the rest works well for you. And then for almost all translation surfaces in this stratum, the translation flow is weakly mixing for almost all theta. For almost every direction. That's the story of weak mixing. And this was one point that was mentioned by Fields Committee when they awarded the Fields Medal to Artur Avila. So he had a few important works, not all of them were in Teichmüller dynamics, but it was one of a few that was mentioned in this summary as his greatest achievement, this proof of weak mixing for interval exchange transformations. Then there is one more plot, a little bit more sophisticated, about the exponential mixing this time, but not for interval exchange transformations, but for the Teichmüller flow. So I will also outline this part briefly. So we will discuss exponential mixing of the Teichmüller flow. So we fix a probability space. For the moment, we will discuss some abstract notions not related to our particular flow. And we take some measure-preserving dynamical system. So then we consider a Hilbert space of square integrable functions whose mean value is 0. And we can consider the following unitary operator that would take any phi and consider its composition with our favorite measure-preserving system. And this operator acts on this space. So if we take two functions from this space, say phi and psi, they would live in this space, then we can consider their correlation coefficient. You apply the operator to one of them. And now, since it's a Hilbert space, you have a way to take a scalar product, and that's what you do. All these properties, the mixing properties that we discussed, they all have an interpretation in terms of this functional analytic definition. So you remember when we discussed ergodicity, we said something about invariant subset that should have full or zero measure. You can replace it by the following statement. You can say that your system is ergodic if and only if for any two functions these coefficients tend to 0 in Cesaro sense. And then you can also explain what does it mean to be mixing. You can say that it's mixing if it converges to 0 as it is. And exponential mixing means that this convergence is exponentially fast. So you have very, very fast, people call it decay of correlation. Because these correlations, they go to 0 very, very fast. And that's what it means to have exponential mixing. And it is very easy to see that apparently if you take all the functions here, it's extremely rare property. It's very, very hard to imagine that it's true for all functions that you take in this Hilbert space. So typically, People require that these guys live in some part of the space, in some Banach space of regular functions that is dense in this part. Because if you want to be true for all of them, it's too demanding. So you will be already happy if you can check it for some dense subset. But since you want to work with some additional structures and functional analysis, you also add some requirements which set it should be, that it should be a Banach space. And in this case, you can require that these coefficients satisfy the condition this is a norm defined on these subsets that we discussed, and you need to add some exponential. And this delta is independent from your function. It's a global constant. And in particular, if it holds, it will imply mixing. So exponential mixing, it's not a spectral notion, because the spectral notion depends only on the properties of this U. So the theorem that we will use to complete this section was proved by Arthur Avila, Jean-Christophe Yocoz, and Sébastien Guezel, and it's the following statement. I will even preserve Avila's name, not to write it for the second time. So it's a theorem from 2006. The Teichmüller flow is exponentially mixing on any connected component of any marked modular spaces. Of course, it's not true that we covered all the cool results in Teichmüller dynamics. In particular, we basically ignored all the connections with billiards and rational polygons, for instance. We did not go much inside into the part about non-uniquely ergodic interval exchange transformations. We just announced the fact that typically they are uniquely ergodic, that there are examples that are not. But we did not say anything about this part, what happens to those who are not uniquely ergodic, how often, from the point of view of Hausdorff dimension, it happens inside of the parameter space and so on. So this part was completely behind our interests. We did not discuss much how to apply the tools from symbolic dynamics to study interval exchange transformations, and focused mainly on geometric and ergodic aspects, while in reality there is a lot of work, and even some of the theorems that we proved in ergodic sense could be shown using the symbolic tools, including the fact that they are typically uniquely ergodic. There is a proof by Bashar-Nitzan that is purely symbolic. We have not discussed much anything about the geometry of the corresponding modular spaces. You had some experience discussing geodesics there, but we did not go much deeper into this part. So, of course, there are many, many things that people are interested in, but we or mentioned it very briefly or skipped it completely. But I hope you got some idea what kind of questions arise in this part of dynamical systems, why do people care about it, and how it's related to the most classical subject in dynamics, the study of geodesic flow. So now we are ready to switch to a completely new branch of dynamics called the homogeneous dynamics, and it will be very, very different. You will not see much of geometry, but on the other hand, at the very beginning at least, it will appear as a piece of algebra more than any geometric plot. So let's switch to this part. We're going to start from the notions that we already discussed a little bit. I hope you understood it, the Haar measure. But now I will require you more details. I recall you in which context we already discussed Haar measures. You remember when we were studying the geodesic flow and we defined the Liouville measure for it, and we were looking for an easy proof of the fact that this measure is invariant. So now it's time to know a little bit more about them. This is the name of our, probably the last section. And we start with a brief recall of our measure. So I state the theorem. G will be locally compact topological group. G admits a non-zero radon measure. That is invariant under left translations. This measure is unique. Up to multiplication. By a non-zero real number. And since I fixed that it should be left translations, then we know that it defines as left Haar measure. I will not prove this theorem. You can find it in many classical sources. But I will provide you many examples because I think it's more important to understand what does it mean physically than to be able to feel all the details in the proof. So the first example, which is very elementary one, we take RD, d-dimensional real space, as a group. And then Lebesgue measure is a Haar measure. Now we can take a discrete group. And then the counting measure is a Haar measure. This is something kind of to the most, elementary and the most polar examples that you can imagine. So they should be something in between, and we provide more examples. The next example is that we consider the following matrices: A, B, A minus 1, 0, because we want them to be upper triangle and to have a determinant equal to 1. So we assume that A is non-zero and both A and B are real. You can check that indeed it's a group. And so the measure that we are thinking about is dA dB normalized on 1 over the module of A. But actually there is an important thing that, of course, you can modify this definition and make the definition of the right Haar measure, right? You just replace all the left translations by right translations. But then it's not at all automatic why the measure you construct should be both left invariant and right invariant. Naturally, it's true for the first two examples, but it does not hold for the third one. And you can easily see that this measure that we wrote here, it's left invariant, but not right invariant. So it's a moment when we can make another definition, introduce another definition, the definition of the modular function. Is it clear up to now what we said here? We already discussed a bit the Haar measures. So just now I recall what was going on. It's clear, right? Okay. So we have a locally compact topological group. And you have a left Haar measure. So we define the modular function. Of G. It's a unique function G to R star such that for any continuous function with compact support, on G, and for any element H of G, the integral over G of the image of GH minus 1 with respect to this measure is equal to the function that depends only on H multiplied by the integral over G of this function. So morally, it means that you can move this H outside of the integral here. And this function is what is called the modular function. It's this guy. How to find this function? First, its existence follows from the previous theorem, because we said that we want our measure to be invariant under translations. And then the second point, how to compute it in some examples. For instance, we take this example, and it's easy to see that in this example we have 1 over A squared. And the group will be called unimodular. if its left and right harm measures coincide. So they are both left and right invariants. You may ask me, as usual in this case, when you get some abstract definitions, can I provide an explicit examples? And it's quite easy. Of course, if you take abelian groups, it's pretty automatic. Because, okay, the left and right multiplication are not so different. So abelian groups can be seen as an example of unimodular group. Then discrete groups also serve this purpose very well. Then there is an example of compact group. The reason is because the modular function in this case is a morphism. And finally, what interests us more is the fact that you may check that SLDR and GLDR, they are unimodular. So now I want to make the following technical observation. We will need to discuss briefly what happens to the harm measure of the quotient spaces. So we take a locally compact topological group. And we have a closed subgroup of this group. And we consider a quotient and ask ourselves, what does it mean that we have a radon measure that is G invariant and not zero? And apparently it's just equivalent to the fact that the modular functions of G and H, they agree on H. Of course, this measure is also unique up to scalar multiplication. In particular, if we have some unimodular function groups, then such a measure necessarily exists because the modular function is something trivial. So if we take a discrete groups, for instance, so H is discrete, then phi GH is a sum over all members of H of this thing. So it's easy. Now, if G is SL2R and N is a set of upper triangular matrices with ones at the diagonal, this is nothing else but the set of real numbers, because it's the only parameter that changes its values. So it's equivalent to take the set of real numbers. And in this case, they both are unimodular, so you can factorize. And this guy will admit an invariant measure. And it's not hard to see that this measure in reality is a Lebesgue measure. Then you can consider a projective line. You can take the group P that we discussed here, here, and you consider the quotient of SL2R over P, and you can see that in this case, this projective line does not admit any radon measure, because this group is not unimodular, as we already mentioned. And now we arrive to the central notion of the whole course, to the notion of the lattice. We already spoke a little bit about the lattices in context of Fuchsian groups, but now our attitude towards them will be significantly different. So it's time to introduce lattices. One more definition. Sorry that there are so many, but it's because it's our first lecture on this topic, so we need to fix our vocabulary. And in the rest, we will prove more theorems or study more examples, and we'll do less definitions. So we have a locally compact topological group. We have discrete subgroup. And so we say that this subgroup is a lattice in G if the factor admits a radon non-trivial measure. So if locally compact topological space that we get after factorization admits a finite radon measure that is invariant under the natural left action. As usual, let's see what's going on in some simple cases that are easy to examine. So if I take you RD as a group, who is the most natural candidate to be a lattice? Who? ZD. You take ZD, and they both are abelian, so quotient is a compact. You maybe even know what is it. And then the measure is finite. So you see the simplest example, when it works, is very easy to imagine. And apparently, we can connect all these statements that we made in the following proposition. If we have a locally compact topological group which admits a lattice. Then G is unimodular. So if we have a lattice, then necessarily our function is, our group is unimodular, and we can avoid to distinguish much how measures the left and the right ones. So lattice is a nice property. The existence of lattice is a nice property that tells us a lot about the group structure. So I think I prove this statement. Then we may have a break, and then in 10 minutes we will resign. So I will try to prove it. The idea is the following. We have gamma, and gamma is a lattice. Then it means that we can consider this factor, and we say that since it's a lattice, it's true that it admits a measure. But if it admits a measure, then we claim that this should be trivial. Assume that there is a kernel of our modular function. Then gamma should be a part of this kernel. And then we can consider the measure on this factor and consider its image of the G-invariant measure on this factor. Then it's a finite G-invariant measure on the factor of that we consider on the IH. So, and this has a finite Haar measure. But then it means it's compact. Now we consider this function, the modular function, and it factors as an ejective morphism. But then there should be no non-trivial compact subgroups. So necessarily this H should be the whole G. So it was a kernel, so we know that it's all trivial. And we don't have anything smart as a modular function. And thus we necessarily have that these two measures coincide. Okay? So the idea is very simple. You just have to consider the kernel of your modular function and consider the following factor and try to analyze what does it mean, and check that in this case your modular function is an injective morphism. It acts to the real numbers, so it should not take some non-trivial values, so they should coincide. Okay, so now maybe we have to make a short break, and then we will resign and see some examples. And my plan for today is to prove the central statement, namely to show that SLDZ is a lattice in SLDR. So today there will be no dynamics. You need to be patient. We will study more kind of algebra and measures. But already next time I will prove you the first dynamical statement in this context. Okay, so let's make a break. Okay, so we agreed that if we have a lattice, then necessarily the group was unimodular. So one more proposition that can be useful. I skip the proof, but it's not hard. So if we have a locally compact topological group, and we have a discrete subgroup, then if gamma is co-compact in G, so co-compact just means that the factor is compact. Then gamma is a lattice. So let us consider a few examples. The first example is the following. We take a Heisenberg group. So Heisenberg group is the following guy. You take 3 by 3 matrices, put ones at the diagonal, and then fill the rest by x, y, z. And these x, y, z are all real numbers. And then you do the similar thing. It will be our G. And as a gamma, the discrete subgroup, we do the same thing, but we say that x, y, z are integers. And then we can consider z formed by h0, 0, z, and z is in R. So all the x and y are zeros. And this is a center of our group G. So it's normal as a subgroup. And we can consider the factor. It will be nothing else than R2, because we have to add x and y as some points where we can vary the values. And since we know that gamma z is a closed subgroup of our group G, so intersections of these people, they are co-compact lattice in Z also. And so we have that this is a compact and gamma is a lattice. And I want to consider one more example. In my notes you will find more examples, but I want to skip some and to consider ones that can be interesting for you maybe, because it's kind of a bridge with what we did at the previous part in Teichmüller dynamics, because I want to consider the surface group. So you take S, closed orientable surface, of genus G greater or equal than 2, and gamma is its fundamental group. So we choose uniformization of S. Uniformization means that we add a complex structure. And the universal cover of S is nothing else but our favorite hyperbolic plane H2. And now we act by gamma on H2. You remember what we discussed when we talked about deck transformations and these kind of things in hyperbolic geometry. So it acts by orientation preserving isometries. And this means that there is an injective morphism. This morphism takes gamma to PSL to R. PSL to R is an homogeneous space. This we discussed when we were talking about hyperbolic geometry and hyperbolic dynamics. And we can consider H2 to be a factor of PSL to R on PSO2. And the S, which is a result of factorization of H2 on the actions of gamma, so it's compact. Thus, what it gives us is the fact that the image of gamma in PSL to R is a discrete co-compact subgroup. But then this proposition that we post here means that it's a lattice. So lattices are really widespread, and you met them much before you started to study homogeneous dynamics. And so for the rest of the lecture today, my goal is to prove that SLDZ is a lattice in SLDR. So in order to do it, I will first study the lattices in RD and then try to apply these results to prove my main statements. So the first proposition. Lambda is a discrete subgroup in RD. So my goal is to prove, maybe I should mark it, goal is SLDZ, a lattice in SLDR. And the first step is to check lattices in RD. So it's a discrete subgroup. Then there exists K that does not increase D, and a linearly independent family of vectors. Such that our lambda is nothing else but a subgroup spanned by this set of vectors. In particular, we know that it's a free abelian group. And so in order to be sure that it's a lattice, it's enough to check that it has a rank D. I skip the proof of this statement. It's rather technical, but not hard. And so if lambda, I will apply it immediately. So if it's a lattice, then we can consider the factor and keep it with unique Radon measure, which is invariant under translations. So translations that are associated with the choice of Lebesgue measure on RD and the counting measure on lambda. So you understand, we want to build a Haar measure. If it's a lattice, we can do so. And it will correspond to the choice of two natural measures in these spaces. And here the natural measure is a Lebesgue measure, and here the natural measure is counting measure, right? So the total measure of this set it's a covolume of lambda. So of the total measure of the quotient. Now every lattice in RD, it's a discrete subgroup, right? So it's an image of some standard lattice that comes from the D. So it's the image of the standard lattice by the element of GLD dr. Now, stabilizer of this of ZD, stabilizer of ZD in GLDR. It's nothing else but GLDZ. So what is the space of lattices of RD? We can associate with a factor GLDR factorized with respect to GLDZ. So the result of it we can say that the space of lattices in RD, you can identify it with the factor GLDR, GLDZ. Right? Do you agree? Because as we discussed, every lattice due to this statement in particular is an image of a standard one, and the stabilizer of this action is given by the matrices with integer coefficients. So you can factorize it. Now, if you add the requirement that the lattices should be unimodular, you replace G by S. Now we can make the next step. So the first step was to understand how the lattices in RD can look like. Now we can make the next step, and it's not related to these particular groups, but it's more abstract. So we prove the following lemma. Please allow me not to prove it right now. Instead, I will want you to be able to follow the general logic of the proof. So all the technical statements, I will state them, but skip their proof and provide the proof at the very end, because otherwise we will be very tired and not able to build up the final proof of the statement we announce. So this will be the lemma. I mark it with a star, and we prove it at the very end of the lecture. So G is a unimodular second countable locally compact group and gamma is a discrete subgroup. It just means that it's second countable as in general topology as a space. It's not a special notion of second countable group. It's in Russian удовлетворяет второй аксиоме счетности. Discrete subgroup of G. So when gamma is a lattice, it's a lattice if and only if there exists a Borel subset S of G with finite Haar measure such that our G is S gamma. This I will prove later, but I will use it immediately. So if in this case we can choose S in such a way that this natural map, so if it's true, if it's a lattice, then we can choose S in such a way that the map from G to G factor on gamma, it's an injective on S. So since I want to prove this statement, I want to prove that SLDZ is a lattice, I can apply this strategy. So I can say that I have SLDR, I have SLDZ, I want to check that it's a lattice, so I need to find such a Borel subset that this condition will be satisfied. So I'm looking for such an S, that SLDR is SLDZ. So the rest of my proof will be dedicated to the explicit construction of such an S. Okay? If you believe in this lemma, it's enough to find such S that we can write this equality. If we give us an explicit value of this S, we give explicit description of S, then we are lucky enough, we can apply this lemma and get the result of its lattice. So my strategy will be to find such an S. I will use more technical lemmas. The next one is the following thing. That this lemma tells us that lambda is a unimodular lattice in R2. Assume that it's the case. Then we can be sure that there is a nice non-zero vector. So lambda contains a small non-zero vector whose Euclidean norm does not exceed one, is the following constant. Looks very artificial, so you will need to be patient to see how we apply it. And we will use it later. But before we proceed, I need one more statement in order to be able to construct S. So the statement is about some classical plot, which is called in the theory of groups, Iwasawa decomposition. So we do the following thing. We fix K, it's SOD. We fix A, diagonal matrices with positive entries. And we fix N as a group of upper triangular matrices whose eigenvalues are all 1. So if we apply the Gram-Schmidt orthogonalization process that you probably studied in the course of linear algebra, you remember it was a way how we can construct an orthogonal normalized basis from the original one. The same process gives us the proof of the following proposition, which is called Iwasawa decomposition. SLDR KAN. So what does it mean? Is that KAN to SLDR is a homeomorphism. So the set S that we are trying to find is nothing else but a product set in the Iwasawa decomposition. So we want to compute its Haar measure, so we need one more lemma, and we are almost done. This lemma I will mark with 3 stars. We equip these guys with Haar measure, and the image of the product map product map K times A times N to SLDR of the measure AGG dk dA dN is a Haar measure on SLDR. And we are almost there. So what we need still? We can consider if A is this set, we can consider the set AT. It's the same thing. So you take elements of A, but you make some kind of order on its elements. So you want it that the following condition is satisfied for any I between d minus 1 and 1. And in a similar way, you do NU. This was the set of N, and in U is the member of the set of N, such that N ij is less or equal than 4. Sorry, than U. Sorry, than U. So this is what NU is called. So they are subsets of A and N that are ruled by some parameters T and U. And so we will construct so-called Siegel domain. It's K, AT, and U. And this is our candidate to be S in this lemma. So we will choose T and U in a way that this set will be this nice S that we are looking for. What do we need from this S? We need that this condition is satisfied, but we also need that this is a Borel subset with finite Haar measure. So I will act in the following way. First, I check that all these Siegel domains have finite Haar measure, and then I choose T and U in a way that this will be true. Okay? So my first lemma is to check that STU for any T and U positive, STU has finite Haar measure. Let's do that. Lemma. So the idea is that we start with d equal to 2, and then we do induction. So first we do it for matrices 2 by 2, and then we run induction on the size of the matrix. So we start with d equal to 2. How does it look like? We consider SL to R and factorize it to N. N is what is written there, these upper triangle matrices. Here we had A, B, C, D. Here we had on the upper triangle matrices, so they should be R2 without 0. The right n invariant set can be seen as the intersection of this guy with Euclidean disk of the radius square root of t. So maybe first I want to mention that SL2R invariant measure is just a restriction of the Lebesgue measure. Now we look at KATN. It's right n invariant set, and it can be seen as the intersection of RT without 0 with a Euclidean disk of radius square root of t. So it's not compact because we have this puncture at 0, but still it obviously has a finite Haar measure. So for the dimension 2, it should be true. Now we want to do it in a higher dimension. So K and NU, they are all compact. You see K is SOD and NU is written there. So it's necessarily compact. And then it means that it's sufficient to check, so they are compact. So it's sufficient to check that we can integrate over AT, the product of AE to AGG, dA, that this is finite. And this A is a Haar measure on A. Now we do it in the following way. We consider the following map. Each A we replace by log A22, A11, log ADD, AD minus 1, D minus 1. So this is a topological group isomorphism. So now we need to look at this guy. And we can say that it's the integral over RD minus 1 of the product E minus SE, etc., minus SG. And this is external, S1, SD. So, and you want all of DS1, DS, D minus 1. And so finally you replace it all by the following product. From K to D minus 1, integral from log T to infinity, E minus K, D minus K, SK, DSK. And this is a finite thing because of the induction assumption. So what we get here is that first we checked the base of the induction and then we used the whole induction. And due to the induction assumption, it was not that hard. So we proved this theorem about the fact that we have necessarily finite Haar measure. And now our goal is to establish this equality. But for that purpose, we will need to choose the precise values of our T and U. It will not be true for all of them, right? You need to choose who are your STU, how it looks like. And this theorem even has a special name. It's named after Hermite. Let us state the theorem. So for any D, SLDZ is a lattice in SLDR, and SLDR is S2 over square root of 3 1/2 SLDZ. So as we already discussed, the second part implies the first one, so we only care about the second one. And once again, we will use the induction to prove this statement. Of course, when D is equal to 1, it's automatic. It's not hard to check. Now assume that we have it for D minus 1, and we want to switch to the result for D. So we take G, that leaves an SLDZ, DR, sorry. And we take lambda, which is G ZD. So then we can take V1, which is an element in lambda with the smallest Euclidean norm. You remember we had lemma 1 there about this, not there, it was, yes, it was here about this thing. And we know that it's a principal vector of the free abelian group here. And so we can find other vectors like V2, etc., Vd, such that V1, Vd is a basis in our group. So this basis, what happens to it? So we can consider gamma to be an element in GLDZ such that gamma sends E1 ED to G minus 1 V1, G minus 1 VD, right? Since you see what happens here, G minus 1, it gives us exactly the D, so we can use only the matrices with integer coefficients. And this is a canonical basis of RD for us. Maybe we needed to replace, since we want here, maybe we needed to replace V1 by minus V1, but it doesn't matter. So in particular, we know that G gamma sends E1 to V1. So there is a K such that V1 is set to A11 A1, and A11 is a norm of V1. But then it means that the matrix Kj gamma has the following form. We have A11 here, something here, 0 ash, and this ash is an element of GL D minus 1 R. So then we can apply the induction assumption and prove the statement for this H. And then we can find L in K by induction. We can find L in K and delta in SLDZ and A22 ADD positive such that our AII will be smaller than 2 over square root of 3 A plus 1, A plus 1. And so our L G delta would belong to the set AN. A here is a diagonal matrix with A11 ADD at the diagonal. And so the only thing that we need to check is that A11 is small enough with respect to A22, right? Because we want the conditions to be satisfied. You understand what we did? We kind of split it into two parts. One was one-dimensional part that corresponded to the smallest vector from the point of view of the Euclidean norm. And in the rest, we could apply already the induction assumption. and they behaved very well. So we only needed to compare the absolute value of our first element with the absolute value of the second one, because we wanted to live in AT. You see there it's written the condition on AT. So we want to be sure that with the required T, these conditions are satisfied. Because for the rest, starting from 2, we have induction assumption. We can be sure that everything works. So now we need to compare A11 and A22. And this is the moment. In order to do it, we just need to apply our lemma that tells us about the norm of this vector. So this 2-star lemma will give us this result. Because A1 is the minimal norm of non-zero vector in this lambda. So when we consider a discrete group given by G delta ZA1 plus ZE2, it's a part of lambda. And then that means that by construction, A11, A22 minus 1/2 delta, it's unimodular lattice in the Euclidean plane. All of these vectors have a norm which is greater than this thing, and so necessarily this lemma implies what we need. So the only thing that we need to check is that our n can be seen as n 1/2 intersection with this. And once again, we will try to use the induction. For d equal to 1, it's easy. And for the rest, we will need to control what's going on with the radius of the corresponding element. And the result will follow from the application of the induction. So let me summarize what we did. We had these lemmas, and we applied first lemma star to be sure that it's enough to check that we have this presentation, S multiplied by SL to Z. And then, in order to check that we have such a presentation, we needed to prove several statements. In particular, we needed to construct explicitly this S, and the fact that we satisfy the condition on the first coordinate followed from 2-star, and the fact that we satisfy the second condition followed from C-star. Okay? And the induction assumption. And every time the induction used on the dimension of the matrices was our key ingredient. So now we need to prove this auxiliary result. I try to do it quite briefly. The details can be found in the notes. It's clear what we did, more or less. So we checked first that indeed we had a finite Haar measure, and we used C-star lemma here to prove that our S has finite Haar measure. And then the fact that we have such a presentation followed from 2 other lemmas. So I will start from the proof of the 3-star. Will be a sketch of the proof, maybe, not the whole proof. So we consider this map. It's a product map, and you take KP and you construct K minus 1P. Now, SLDR, this person, it's unimodular. So the inverse map of a Haar measure by this map is a measure here. We can consider the pullback of the measure. It's a measure, and it should be right K times AN invariant. So that's a product of the right Haar measures on K and on AN. But K, it's a compact set. It's SOD. For compact people, Haar measure is unique. Left Haar measure, right Haar measure, no difference because it's unimodular. So we know that its right Haar measure is also left Haar measure. So the only thing we need to check is that the product of GG, DA, DN is a right Haar measure on AN. And here we just apply the direct computation. Namely, we can see Dn as a product of DNAIG. N is a normal subgroup here. So the adjoint action of an element A multiplies the measure exactly by this product of AGG, AII. So the result follows. This thing with 3 stars, we checked. So what was the logic? Once again, it's easy to separate K because K is compact. So it's unimodular, and we understand very well how the Haar measure acts. And it was enough to check what happens on A times N. And on N, we have this as a measure, and it's now a normal subgroup. So it's enough to see that the adjoint action is this one, and that's it. Now, what about 2 stars? Two stars is this statement that we can find vector that is small enough. I recall you where we used it. We used it at the moment when we needed to compare A11 and A22 in the proof of Hermite theorem. So we take V, and we say that V is non-zero vector with a minimal norm in lambda. So if the norm of V is smaller than 1, we are done. There is nothing to check. We are happy people. But if it's not true, so the norm of V is greater than 1, then we can consider D. That will be an open disk with radius V. And by assumption, V was the smallest vector. So if we consider intersection of D with our lambda, we will have only 1 point. And since V is a primitive vector in a free abelian group, then as usual, we can find another part so that together they will give us a basis. But then if it's a basis of our group, then we can say that the determinant of VW is exactly plus minus 1, because it's a orthonormal basis. But then what it means that we have an element, so this guy contains an element whose distance to RV is 1 over V. Now, the set E of such vectors is the union of two affine lines whose intersection with D are intervals of length like this. And it's stable under translation. And so what we can say about it, that it should be smaller than V, because it should not encounter D. So it should be inside of D. And then this should be true. And it follows that V is smaller than 4 over 3. So once again, we prove that there is such an element. We consider all the elements with this property, and we see that there are two affine lines. And when they intersect with D, we get intervals of this length, but then they should sit inside of D, so they should not increase the diameter of D, so there should be such a statement. And that's what gives us this estimation. So the very last thing that we are still missing is the proof of 1 star. This statement that allowed us to replace the study of lattices by the study of this product. So I comment on this, and it's the last thing for today. So assume that such a set S exists. We want to prove that it's a lattice then. So if it exists, then we know that for the vector spaces, we can do this. Here, the phi bar So what is our plan? Very simple. S exists, so it has indicator function. So we can take it to be phi to be an indicator function of S, and we will apply this formula here. So since we know that our G is S gamma, then we have no doubts that this phi bar is greater or equal than 1 on the factor. And so since S has a finite Haar measure, then we can be sure that this guy also has finite G invariant measure. Okay, so this is in one direction. If we have such an S, then necessarily it's a lattice. Because what we need to make it lattice? We already have that it's discrete. So we only care about the covolume of the factor. So we need to check that it has a finite measure. In order to do it, we take phi as an indicator function, apply this formula. We see that since we have such a presentation, then our phi should be at least equal to 1 on this part, because S is included in this part. And so then we can be sure that if you can estimate it from below and you still have to get something finite, then the volume here should be finite, because this is not smaller than 1. You integrate over this set. If this set has infinite measure, then you are in trouble, because this will not be finite, and you know that it should be finite. So this is in one direction. And now the opposite direction. So we need to construct such an S. We first construct a Borel subset S of G, such that G is equal to S gamma, and G to the factor is injective on S. And then we will check that this S has finite higher measure. So gamma is discrete in G. That means that for any element of G, there exists an open neighborhood UG such that H to H gamma, that then gives us a map to this factor, it's injective on UG. It follows from the fact that gamma is a discrete subgroup. But then we also know that this guy is second countable. So there should be a way to find a kind of a cover. So there exists a set of GK elements of G such that the union of UGK covers G. And then we have an explicit candidate to be S. S is constructed as follows. You consider union over all K, UGK, without the union when L is smaller than K, UL gamma. So then this S, it's easy to see that the main conditions are all satisfied. And in particular, it should have a finite measure for the same reasons as here. Because if you take an indicator of this S, then phi bar is equal to 1 on the factor. And if this factor has the finite G-invariant measure, then also S has G-invariant finite measure, for the same reasons. So we can construct it explicitly. I think we are done. So today we started to learn a few things about lattices and proved our model example. We proved that SLDZ is a lattice and SLDR. And next time we will start to find dynamics related to the action of these groups. And we'll play with this baby example a lot. Thank you very much for your attention.